Log on, tune in, find out. Another good idea from Cambridge.
Speaker who's going to give highlighted talk with the idea that we keep all the audience to the end of this workshop was chosen to be Martin Burger, winner of the Calderon Prize and professor of Münster University, who has been done extensive work on different aspects of medical imaging, in image restoration, in image processing, and in semiconductor research. Please.
Yeah, thanks for the invitation and well, this nice opportunity to give a highlighted lecture. I must admit I had the same trouble as Rainer Kress. I was not sure what does it mean to have a highlighted lecture. At least I learned from his lecture that I should give a lot of homework, so I tried to put homework for everyone in my talk. And the other thing I updated constantly during this week is I eliminated more and more mathematics and added more and more pictures, since I thought you would be probably exhausted by Friday afternoon after having all these very nice talks and very detailed talks. And the other thing is, probably after having heard these talks, I will not be able to impress you by complicated mathematics anymore. So I try to impress you by images, which is the other way that I do. So I use more the slides maybe that I use for the MDs than the slides that I use typically for the mathematicians today. However, I think it's important for you also to see that all these inverse problems, all these things are really important, and they are really used a lot in practice, and they will be of increasing importance in practice. So biomedical imaging is something that is now around everywhere. There is a quote that I found, which is already several years old, which says that only in the US 300 million of X-ray, CT scans or MRIs are done each year. Probably this is much higher already by now. And this is a number which is still going up, because the current trend in medicine is what they call personalized medicine or individualized medicine. So people would not take just your risk factors, say, are you a smoker, are you eating healthy or things like this, but they would really try to say you should do something that predicts the individual chances, for example, of getting a heart infarction or things like this, and try to get individual care, individual pre-care done, and all this is based more and more by medical imaging. And not only in the clinic, also in the preclinical and biological research, nowadays imaging is really the driving force. Everything that they do in biology is somehow relies on some kind of image data or some observations, and what would be a proof for a biologist is something that he sees on an image of an experiment, something that he can document by imaging data. So images are really important, and good imaging techniques are really important. So the first thing is to explain is it's very easy to explain why MDs love inverse problems, and for them it's very easy to understand why inverse problems are hard, because basically they solve inverse problems all the time. When they do diagnosis, it's just solving an inverse problem. So the symptoms are the very indirect data that they get about the disease, and they try to figure out what is the unknown observation without going inside. So the typical problem that somebody in a medical department solves would be an inverse boundary problem. He observes things on the outside and he tries to figure out what is going on inside without opening it. There's one thing that you should be very careful in this translation. When I started to work in medical imaging, before I was mainly working in engineering, semiconductor stuff, things like this. When I went to the first conferences and talked to people, or talked also to the people in Münster in the med department, they were always talking a lot about models for diseases. So I thought, oh, that's cool. They have their models, so probably they have some PDs or some other nice things I can compute and I can start with. It turns out, if you ever hear something in a med department speaking about the model, be careful. This is typically some genetically manipulated animal, a mouse or something like this. So this has nothing to do with what you're used as model with the mathematicians. However, it is possible to talk nicely also to these people in the med department. So what is the classical medical imaging? Well, the classical medical imaging nowadays is X-ray based. So X-ray, the old techniques, and already classical by now, the techniques developed in the 60s, 70s, computerized tomography, as Samuli has nicely explained. This relates to the inversion of the radon transform. So you get images like this. So this is a human CT, this is a small animal CT, these are the typical things that you get. You see you get static images with a pretty high spatial resolution. They can be made very sharp. There is a very low SNR, so this is pretty nice on the one hand. On the other hand, it's not so easy for several tasks, in particular if you want to follow diseases, because it's only static. You cannot do a CT over some minutes or hours, because you would just burn the patient, and you would just, well, first of all, you wouldn't be allowed to do it by law, but it would just be too harmful for the patient. And the mathematics is also very classical by now. Of course, as an Austrian, I have to mention Johann Radon. Johann Radon solved these inverse problems in 1917, and later became, by the way, president of Vienna University. This is also something that frequently happens in Austria. And you know, if you want to learn this, there are classical books, in particular the one by Frank Natterer is really the classic book on to learn how to do these things. And I have to say, although there's this story about Radon inventing this in 1917 and McCormack redoing everything in the 60s, it's not completely true, because McCormack was doing some numerical approximation of the Radon inversion. These Radon formulas, they were actually discovered in the 70s or 80s, and they were still the basis of developing new analytic inversion techniques and explicit reconstruction formulas. And indeed, CTs may be the only field in medical imaging where they use more or less explicit reconstruction formulas, because they can do the SNR so low that the noise is not a big problem. So there's no issue about all these regularization things and this, but they can really plug things very nicely, do a bit filtering on the data, and then plug it into exact reconstruction formulas. And this is why they get also very fast reconstruction methods. Okay, so this was the 20th century. What is the 21st century? What would you learn from a radiologist, from somebody in nuclear medicine about 21st century imaging? And what they would tell you is, now imaging should go beyond anatomy. It should go to physiology. It should go to the dynamics. It should give you, like this MR of the beating heart, information about processes going on in your body. Or it should give you, like these PET images, quantitative information. So this is a combined PET CT image that shows the aorta and some PET marker that quantifies an inflammation in the aorta. So this is what they mean also by the word that frequently is quantitative. They want to understand quantitatively not just how is the anatomy looking like, but they want to understand how harmful can processes be, what biochemistry or things like this can appear that can be harmful or that can be good for the cure if they are monitoring, for example. And there are many emerging techniques like PET, SPECT, optical imaging. This is an optical imaging technique. MR or variants of MR, ultrasound is, well, already a bit classical, and then there are some crazy things like Raman spectroscopy or Carr spectroscopy, which are even based on some crazy quantum effects, which I wouldn't even dare to explain how they work. So if that goes on, yep. So the vision, as I said, is to get quantitative and dynamic imaging and to get it in vivo. So what you would like to have, for example, in a cardiovascular application, you would like to follow the biochemistry and the mechanics of the blood flow, and you would like to understand, for example, if you have some troubles in like a plaque, you would understand, is a plaque harmful or not? So the first step you would say anatomically, okay, it makes the cardiovascular wall smaller, so it might be harmful. But if you know already a bit about fluid dynamics and about biochemistry, you know it's not automatically the case. A plaque does not automatically mean that you have troubles or that there is a rupture in the wall. There is a lot about mechanics and biochemistry that you have to understand to quantify how harmful such a plaque or things like this could be. And this is why people are more and more going into what is called molecular imaging. And also to clarify this, molecular imaging does not mean imaging single molecules. It just means still macroscopic imaging typically, but it means you mark certain molecules by some tracers. So you would put, for optical techniques, you would put fluorescence molecules, so which you can biochemically attach to the interesting ones, or radioactive molecules for emission tomography and nuclear medicine applications. So let me go to the first technique. I will go a bit through several techniques and explain a bit what kind of problems you will face there. And if I have time in the end, I will get a bit more detailed about positron emission tomography, which is what we do a lot. So MR gives images like this. It also depends how you weight MR images. They basically is based on the magnetic relaxation of certain molecules when you apply magnetic fields and remove them. And you can then measure some electric signals that you can easily translate into images. What you have mathematically in MR is the classical problem is the reconstruction of a density function from Fourier samples. So ideally you would say MR measures the Fourier transform of your image. So this is something that for inverse problems doesn't sound really interesting, because inverting the Fourier transform is not even an ill-posed problem, and you can do it now with FFT with many routines, so there is nothing that you would think is really interesting. However, there is still a big issue in MR, and this is that MR is really slow. And MR machines are not very wide, so it's not nice for the patient to be inside there. And due to these magnetic coils rotating around, these things are really very loud also. So many patients have real troubles to be for longer time inside an MR machine. So most of the research in MR also goes towards making it faster, also due to time resolution, but also to just get the measurements done faster. So what you would like to do is reduce the number of measurements. This is what all the compressed sensing people would tell you about. So don't take all the Fourier coefficients, but only take few of them and try to reconstruct the image with some a priori knowledge. Then there are, if you measure fast, you have some distortions that you might need to correct. And finally, in image analysis, a big issue is how to segment these MR images, because the contrast is not so clear as typically you had in CT. So what you do nowadays, and what is really, there's a variety of open inverse problems, is what some people also call nonlinear MR. So the classical linear MR would be to reconstruct this density function rho here when the coil profile is known. So basically you could also reconstruct the product of these two, and when there is no field inhomogeneity and no relaxation, or when the relaxation is fixed. So then we could subtract these two things. They would basically be constants that you can subtract from this. So basically what you would have is this thing you go through this K-space. This is the trajectory that you go through with your MR. This comes from your magnetic field. And you can easily read, so what you have a function of R, and then you have E times K times R times 2 pi. So this is exactly the Fourier transform of this thing here. So the classical linear problem is invert the Fourier transform if you go through enough K's here. However, if you measure faster, or if you do fancy things with the relaxation, then you should not only reconstruct this density, but also reconstruct other things. For example, if you measure really fast, then these coil sensitivities, the coils move fast, so they cannot be calibrated nicely. So you don't really know this thing here. You just know an a priori guess for this, and you should not be too far away from this, but it becomes important also to reconstruct these two functions here, which is of course a very hard problem, because you can imagine it's like reconstructing a product, or having a product and reconstructing the two factors that make up this product. However, there are ways to do this quite efficiently, and then the nice thing is that you have a priori knowledge how things should look like. And the a priori knowledge typically is that the density image has pretty sharp edges, because the objects have sharp edges, while the coil is just a smooth perturbation, so of some given coil sensitivity. So there are many methods now to try to decompose a product into something which has sharp edges and something which is smooth and close to something given, and to get nice results from this. And there are indeed work, for example, in Göttingen, who really can show improvements in fast MR by doing this. And then there are also other things where you have, it gets a bit more fancy. For example, if you try to reconstruct also the relaxation here, then you see you have an additional exponential nonlinearity in this reconstruction. or if you construct the field inhomogeneity, this is the W here, you get another inverse problem, which is again nonlinear, and all of them are really interesting and really not very well understood problems, although there are several practical approaches to do this. So this is homework 1, of course, solve all these problems nicely so that you can do fast MR measurement. Okay, the next thing, optical imaging, is very easy to understand. It's just like taking a laser pointer and putting it to your skin. So you can imagine, if you've ever done that, you don't see very white inside. This is just because the optical light is scattering a lot. So it's really the large scattering limit. So what you can do is basically things which are just close to the skin. So for skin inflammation, this is a pretty good technique. For small animals, you can do a bit more because they are either small enough, or since biologists do crazy things and make small animals translucent or partly translucent by some genetic techniques that, well, I don't want to talk further because this is a bit crazy thing, however. So the mathematical problem typically that you face in optical tomography is quite also related to what you heard in the first part of the week. So basically you can model things in the high diffusive limit just by an elliptic equation, and basically what the things that you would reconstruct from boundary measurements again is the diffusion coefficient and also some damping coefficient here, probably by varying frequencies, so the omega here could be varied, and then you get boundary data from this and you try to reconstruct these two things. And there are several reconstruction algorithms for that. In particular, I think also Simon Erich in London has done a lot. And I should also mention that there is still not only, this is not the ultimate equation maybe to use. In particular, the group of Guillaume Ball has done a lot on improved modeling using kinetic theory and better transport models to get better reconstructions for this type of problems. But you see, from what you learned, you see this is quite an unstable reconstruction problem. So you cannot think about too much quality in your reconstruction, and you can immediately see how this high instability behaves in practice. Just take the laser pointer and put it to your skin and try to figure out what is inside. You see the information is really highly damped. So there you see, well, maybe in practice, what means bad instability. Okay, when you mention optical, you should also mention microscopy, which is something that is usually considered a task for image analysis and not so much for inverse problems. But microscopy, however, is important because it's really the workhorse nowadays of biologists. They do all kinds of crazy microscopy, and they do all kinds of crazy fluorescent microscopy. So they have these green fluorescent, red fluorescent, blue fluorescent proteins that they can use to label certain parts of the cells or cells as a whole. And then they can follow, these are germ cells in development. They can follow the cell boundaries, they can follow intracellular, so blue typically is the nuclei, and then they can address some other specific intracellular proteins that they want to understand what they are doing in certain biological tasks. So the mathematical problem here that is left typically is just the deconvolution problem. So you had this also, I think, in Samuel's talk. It's like in any optical, also in a camera image. You have a slight blurring of your image with some convolution kernel, and you try to reconstruct the image, which is nowadays pretty well understood, and there are many algorithms for this. Even the microscopes, they have their deconvolution algorithms. So mainly this is done, if it works well, this is done in the machine and you don't have to do anything. So why am I mentioning this? Well, there is still a lot of things to do. Of course, there is a lot of image analysis on these kind of images, which I don't want to go into detail. But there's also some things that are very interesting if you have fancy microscope and if you have some high resolution situations. Because you face situations where you have a low illuminations and low SNR, so then it becomes important to model how the noise is created and to incorporate this into your reconstruction. The trouble is not the typical kind of Gaussian noise that you have seen and that is typically modeled as the simplest noise model. You add Gaussian noise to your measurements. What happens here is you have to incorporate a Poisson process or a Poisson statistics, because basically you have few photons, you have a counting process, And this can be modeled by a Poisson process, and this has to be incorporated into the reconstruction. Another thing is, in fancy microscopes, is kind of blind deconvolution. It's not always clear how the kernel looks like, and there may be also phase distortions that you want to correct by this kind of reconstruction. So this leads again to nonlinear problems. And the final problem, which is hardly investigated nowadays, but which I think is really important, is to relate these images, or even particular dynamic microscopy, to real mathematical models that give you understanding about biology. I'll give you just one example. Oh, first I show you some images. What you can do with a bit deconvolution and TV. Okay, it's not really impressive because the beamer is filtering out a lot on both images, so they look pretty much the same. So this is what you could do with these total variation techniques that Samuli mentioned. So maybe the second one is better. Yeah, maybe at least here you see something. So this is a data set that you get from developing neural cells, where you see you have a lot of noise and you have some blur in these effects. What, for example, they want to do here is they want to do some shape analysis, and when you do a bit deconvolution and total variation regularization, so you get very sharp objects and really geometries whose shape you can analyze afterwards. EM is expectation maximization. We'll come back on this later. So the EM is basically the correct thing for modeling the Poisson noise. So it's not this quadratic term to match the data, but a different term to match the data. I will come back on this hopefully later. Okay, just to mention what kind of inverse problems you would like to see. So this is for crowded cellular motion. So these are germ cells during the embryo development in a zebrafish. And this is some flow images. Here we computed also some flow fields of a single cell, so where you try to focus inside the cell and see what's going on inside. And the biologists try to understand how is this motion going on, or how is also some intracellular motion going on. So what you can do is, as you usually do, you can build up mathematical models for motion of cell populations or of subcellular populations. And the trouble you get is that you are in a highly, as you see here, you are very often in highly, oops, I'm going the wrong way. You're often in very highly crowded situations. So if you are experienced in mathematical modeling, like deriving macroscopic PDEs like Boltzmann's equation or even further diffusion equations, you always have some kind of mean field limit which says you should not have too crowded particles. So exactly this is the situation where the standard macroscopic limit to PDEs has troubles, and depending on specific assumptions you make, you get different models, and the models change basically in two things. It is the diffusion coefficient, which can have different nonlinearity, and a mobility coefficient, which can also change. So the classical mean field limit would say that the diffusion coefficient is constant and the mobility is linear. So this is what you automatically get from Boltzmann, for example. However, then people do investigations and do statistics that predict how would the diffusion be in such crowded situation intracellularly or extracellularly, and then they found out there is a lot of anomalous diffusion. So it does not scale like a linear or a constant diffusion coefficient would predict. And so you have to really go to find these things. In particular, you would expect in highly crowded situations that you have some saturation of your mobility. So if you reach a maximal density, then nothing would be able to move. So this thing should at some point not always grow like this here, but there should be a regime where they start to go down again. So the interesting inverse problem, maybe this is the homework more for Gunther and Adrian, is Gunther is getting interested. I see. What you would like to do is, from data about these images, you would try to identify both these nonlinearities simultaneously. And then the question is, what are the data? And this is also not completely clear, I would say, because there are at least three approaches that people make from these images. The first thing you could do is you could, like we did here, in a more or less automatic way, you could try to estimate trajectories. So this is what cell tracking is all about. It basically gives you trajectories of moving cells or of moving intracellular things. So this would mean you would use inherently stochastic things to invert for a macroscopic PDE. The right thing to do is you would interpret the solution of the PDE that we had on the last page, the U. You can interpret this indeed also, if you rescale it appropriately, as a probability. So this density is also a probability density when you rescale, and it gives the probability of a particle being at space x at time t. So this means you could do something like a maximum likelihood estimation based on interpreting this U as a probability measure. You could, however, also do other things, and my colleague Christina Surulescu with her husband did a completely different approach to go towards macroscopic. What they used is they took these trajectories and immediately applied a classical thing in statistics, namely density estimation. So this is a typical trajectory, and these are different time steps of estimated density. So this would be, of course, the nicest thing maybe for the inverse problem, because this would be a distributed measurement of U. So these are time snapshots of the solution U. And of course, then it would be very trivial to prove things like uniqueness if you use this data. But on the other hand, you don't know what kind of error you introduce by going from these trajectories with this density estimation to a macroscopic thing. Okay, the final thing, which seems to be really, which we were looking a lot into, since this is a genuine way of getting macroscopic data, is to use flux measurements. So basically what you do is you put maybe some line here and you count how many particles are crossing this line per time interval. And this is what you do, for example, when you do electrical measurements also. And this is also what you would do in practice when you do traffic counts. When you do traffic counts, you take your road, you fix a line, and you look how many cars are going through per time. So the flux is something very natural and macroscopic. It's already a macroscopic quantity. And then this leads to a very interesting problem, namely a boundary value problem again, or an inverse boundary value problem to get this data from different fluxes. And I also forgot to mention, you can, of course, try to vary things in these systems. For example, biologists can vary things like a chemotactic strength. So they can put some signals that things are cells would follow, and they can vary the strength of the signal. So they can, for example, put a constant here U, capital U, which they would vary. So actually this is not a single PD that you're using, but this is like in a tomographic setup. You have many of these problems and compute the boundary data and try to infer what is going on inside. And there are many other problems like this. For example, there's a lot of reaction diffusion models in biomathematics, where actually, if you're honest, you don't really know what are the reaction terms. So if you would really be honest, you would identify all the reaction terms, all the nonlinearities from data that you get in this way by images. Okay, another thing which I don't have much to say is ultrasound. Ultrasound is also very classical. It's basically, you heard all about these inverse scattering type things. The only thing I have to add is, so this is, as you heard in several talks this week, it's an inverse problem basically for the wave equation with some sources, which is the emitted ultrasound waves, which you can also reduce to the Helmholtz equation, as you have seen. The only thing I have to add is that it is not common nowadays in medicine to do reconstruction. So basically, they just use the echoes that they get from the ultrasound, and they look at these images, and they can look pretty crazy like this fetal image here. So if you get a child, or most of you are young, so maybe you will have this in the future, then you will experience what it means to do ultrasound. You go to your doctor, he will tell you, well, I see this and this and this, and it's a boy, and you will say, okay, I don't see anything. Can you give me the raw data? I want to reconstruct. And when you learn to do this, you can really try to do it and figure out whether your doctor is right or not, or you just wait for several months, then we will see what's going on. Okay, and then the novel trend, of course, is, as I think Gunter Ullmann has explained a lot about these hybrid things, which is photoacoustic or thermoacoustic imaging, where you take the ultrasound and you modulate, for example, by some lasers or by some thermal effects. And then, for example, you get reconstructions like this took this from a recent paper from the NCA Christos group. They are one of the leading groups in experiments there. And this is some animal cardiovascular structures that you can very nicely reconstruct even with time resolution, as you see from the time arrows here. Okay. So something else I should mention is electrical imaging, which is also not, well, which is a matter of discussion whether you should call it imaging. So the typical people doing like CT, they would never think this is imaging, but cardiologists would hope that this becomes imaging. So what you would do as a first thing as a cardiologist, if a patient comes, you put the ECG electrodes and you measure electrical signals all the time. So they look like this. Okay. So what the cardiologist does, or even his assistant, they look at this signal and say, okay, in this electrode it should look like this. Does it look different? Maybe then he has some disease. This is of course not a very quantitative way to go towards a cardiac disease. So what you would really do, we would like to do, is to measure not only these few electrodes, but to measure many electrodes over the whole body. These are so-called body surface potential maps. You would get maybe a CT in the US or an MR in Europe, because we are a bit more caring about radiation dose, so we don't do so much CTs. You would reconstruct the anatomy of the patient here. So this is the torso, you see the heart inside. And then you try to solve an inverse problem, going back from this electrical data. Because what you know is, basically you have Neumann boundary data. You should have more or less insulated torso. So on the torso, the Neumann boundary data are 0, and you have the potential, so you also have Dirichlet boundary data about your electric potential. And then you know more or less it's the electric potential solves the Laplace equation, or some anisotropic version of the Laplace equation inside the torso. And then it's classically to compute back from the torso to the heart, so torso surface to the epicardial surface, which is the outer surface of the heart. And the group of Yoram Rudi in now St. Louis, I think, has made this popular among also cardiologists, and they even did some very fancy way of validating their data. So they have some cases where they could intraoperatively in a dog, not in a human, measure really this epicardial potential. So you can have a sock of electrodes that you put over your heart and measure these things. So they have some good results on this. Although, again, you see this is an inverse problem for an elliptic PDE. So it's a Cauchy problem basically for the Laplace equation, for an anisotropic Laplace equation. So this is a very unstable problem. So this is a real trouble to do, and this is why it's not yet standardly used in clinics. And what people currently are trying to do are two things. One is, like the Rudi group is trying a lot, is to get improved priors for the regularization. So to introduce prior knowledge about the epicardial potential. And what several other groups are doing is try to do something different, is not to look at the epicardial potential, because that's not what cardiologists care about. They are not caring about what goes on the heart surface, but they care what's going inside the heart. So what you try to compute is the so-called transmembrane potential. So what you have, if you extend, you have the torso part where you have this more or less Laplace equation with some anisotropy. And then you can build in the heart the so-called bidomain equation, which is a nonlinear system of PDEs and ODEs. And you have two things there. You have two potentials there because you have some kinds of cells. And there is always a change between the intracellular and the extracellular potential. So you write down a system of PDEs for the intracellular and the extracellular potential, or as I wrote down here, for the transmembrane, which is just the difference between intra and extracellular potential. And basically you have some kind again of Poisson equation, and then you have some parabolic equation for the transmembrane potential, where you get some additional parts from so this is an additional current that comes in here, and the current solves some other model equation, which are, there can be like 90 ODEs in each space point or things like this, which model the behavior of ion channels in these cardiac cells. So this is a really complicated problem to solve for. And you could say, for example, if you look for regions that are not intact, you would try to look for regions where this ion current deviates from its normal state. So where some of the channels are broken. So you would put, for example, a distributed parameter in front of the eye and try to reconstruct this distributed parameter. But this is a heavily nonlinear problem. It's computationally a mess, so nobody really does it. We did it for a 1D heart once, but 1D hearts are not very interesting in practice, so this is a bit far from clinics. Yeah, what I should, so this is what I just explained. So what several people are trying now is to do something else, is only to use one of those equations, namely the one which is reasonably nice, the elliptic one, so this would be the extracellular, this is the transmembrane potential. And what you try to do basically is you compute this equation, you know, you have a boundary condition for this, you have also the Dirichlet boundary condition for the epicardial potential, because this is what you reconstruct basically from the body. And then you try to compute W. And you see immediately you measure a function on the boundary, and you want a function in the interior, and this has a huge null space. So the problem is, you can show this problem is more or less stable, because given U, you could solve for W. So this is a stable problem. There's no real trouble with the ill-postness, but the trouble is the null space. So how would you eliminate this huge null space? The nice thing is you basically know, at least during the polarization of phase of your heart, how the transmembrane potential looks like. It looks like a step function. So it steps from A to some other value B, so H is the Heaviside function, at some activation time tau of X. So what you could do, and this is also in epicardial imaging a classical thing, is go from the potential towards the so-called activation sequence and try to reconstruct the activation sequence from your ECG data. And this means, if you go back just to simple inverse problems, what you would need to understand is if W is a piecewise constant, so this has the value A in some part inside and the value B in the other part, can you reconstruct this domain from this equation? And the interesting thing is the anisotropies of the intracellular and the extracellular space, they really should decide this problem. You can easily show if there is no anisotropy, so if these are just constant, then you cannot do anything. Then W is completely invisible to the measurements. This is a 2 minutes calculation you can do. So the interesting thing is there is a lot of anisotropy. So this is a visualization of the 3D anisotropy, the fibers along which electrical signals propagate in the heart. And you see there is a lot of anisotropy, so under which conditions on the anisotropy can you reconstruct these transmembrane potentials uniquely? And there are many people trying to use that now, even in clinics, but we have no idea basically if this is reasonable or not. So if there are reasonable conditions where we can do it or not. So we have one example with Björn Nielsen where we can produce, at least that it produces non-trivial measurements, so it's not completely in the null space, but this is so far all we can say under reasonable conditions. We cannot say that there's anything like identifiability for these things. And by the way, this is done also, this is also a nice story about these anisotropies. This is created by a cardiac surgeon in Münster. He's retired and now he spends his time on blowing up pigs. So he blows up the pigs so that the heart gets expanded and all these fibers get really visible, and then he puts them into a micro-CT, and then he gets these wonderful images of the heart anisotropies. So these are really direct images of how the heart looks like. Okay, and the same problem appears in brain imaging. There you can use also magnetic data with this device plus the electrodes, and basically what you do is a similar thing. You have the equation for the electric potential and you want to get sources. It's even a bit worse there because you want to get a vector sources reconstruct there, and again you see this is highly underdetermined if you only have boundary data, and again you need appropriate model of how the sources would be there, and this is also point-where sparsity and things like this L1 come in a lot. Okay, so finally is what I do most of the time is PET SPECT imaging, emission tomography. What you see, these are the same images that I showed in the first slide for CT. This is now with the PET machine. You see they look completely different. The spatial resolution is much worse, but there are things which are shining very brightly, and this is where a specific tracer, in this case radioactive sugar, is going. So the sugar is consumed where the metabolism is very active. So for example, in a tumor, there should be some tumor here, I think. So you can quantify by the brightness of these spots, you can quantify, for example, how active a tumor is. And this is really important, not just to see a tumor, but to understand, is it really an active or is it a not active tumor? Okay, but there are also other tracers like radioactive water, which you see here, and these are the standard reconstructions that they currently do. This is what they do for blood flow evaluation, and you see, well, with some creativity, you can draw a heart around that, but I would say I see nothing in these cases. So there are really challenging things where you can do something as a mathematician. There are cases where they don't see anything, honestly. So anything you do with improved inversion will help them a lot. Okay, so this is how it works in emission tomography. You prepare a radioactive tracer. So for PET, this is quite expensive. In a cyclotron, for SPECT, you can do it very reasonably. Then you inject the tracer into the patient, and, or in this case, the small animal. And then you put this small animal or the patient into your detector. Will come immediately in the movie. And then what goes on is these radioactive things, of course, they are unstable. So they start to decay. And when you have a radioactive decay, for some of these elements, they will emit a positron. Well, all of them will emit a positron. What happens is the positron will quite immediately hit an electron and they will annihilate. And the energy of the positron and the positron and the electron goes to two photons. And the photons, they go out in opposite directions. And this is what you can measure. And you see what happens here. Here are the photons coming. And what you detect is, oh, there is a photon coming in at this point and this point at the same time. So there was a radioactive decay on the line in between. So what you measure is basically things about line integrals again, because the radioactive decay is proportional to the density. So what you do is a stochastic sampling of all those line integrals. So you're again back to the radon transform, but you have stochastic samples only about it, and you have random directions, because you cannot say how are the directions, it's just how the photons are coming out. Okay, and this is our model with Poisson statistics, and this is really crucial also for getting good reconstructions to model these Poisson statistics. Yeah. And this is then how it goes. Okay, so you do these measurements, and this is also what I took from the web page of our institute. You see the color shading. This is on the beamer is even worse than on the screen. So this is the dark area. You maybe see some people sitting here in front of a computer. So this is the reconstruction, and probably this is the way the people in medicine also see it. So this is the thing where the dark miracles occur and then some image comes out. So this is basically our work in doing inverse problems. Okay, so what you do have really in, just to mention, I will not go into detail. What you really have is this operator K, which is the radon transform, but you should also, if you do it nicely, you should also do some scatter correction and some other corrections. So basically you have to model some two additional operators, one before and one afterwards. So the operator before is like a beta convolution operator, and this is due to the fact that the positron is not immediately hitting an electron, but it travels a bit. So you have a bit of decay, and this is also, you have to also model this stochastically and get like a blurring operator for this, and then you have the scattering with the detector. You have another operator here. But okay, just to show you, Thomas Kösters did this very carefully in his PhD, just to show you what you can do by carefully modeling your forward operators into the inversion. This is the standard only radon transform reconstruction, and this is an improved reconstruction with scatter correction and all these kinds of things. So you can really get much better reconstructions without. In particular, you can eliminate all these artifacts outside the body where nothing should really happen. And there are many challenges here, which is not only PET, but in many things. Since you automatically measure 3D in PET and you measure dynamically, what you have is you have a lot of dynamic reconstruction problems to solve. So this is for the British people who like all this metrology stuff. It's like the 4D VAR a bit. So it's the 4D variation problems that we solve. Of course, you have low SNR in all these problems. You want some quantitative analysis. So you want to couple these two mathematical models. You have in many of these problems, you find underdetermination. So I've shown you many examples. So you have to introduce prior knowledge into the models. And in many of these things, you have some uncertainty and you have some stochastic effects, which is perfectly illustrated in PET with this random decay. So you need to do a good stochastic model about these things. So just to show you a bit what you would have to do instead of just solving Tikhonov. So you would set up your operator like the Radon transform between Banach spaces, or you do some finite dimensional approximation which comes from some sampling or averaging. And then in finite dimensions you can write down very nicely models about statistics. For example, you could do maximum likelihood estimation, so you maximize the probability that U is the image when you observe the data F. If you do it in a Bayes fashion, you would do it in the way you do regularization, so you would introduce the posterior probability. So you have a forward probability of getting F if U is the right image. So this is basically your model of the process plus the random noise model. And then you have the a priori probability, and this is basically the regularization. So what you do in the end is you take, of course, not maximum likelihood, but you take the negative logarithm and minimize it, and the negative logarithm of P would then be like the regularization term in a variational method. So how does this look like? Simple example, let's take additive Gaussian noise. So if we have measure in each pixel, and then we get additive Gaussian noise with mean 0 and variance sigma, you can just look into your statistics textbook, or look into Wikipedia nowadays. Probably nobody looks into textbooks anymore. Look into Wikipedia and see what is the formula for the Gaussian distribution. It's E2 minus this noise, so the noise would be the deviation, divided by the variance squared, and you get this probability here. Then if you take the negative logarithm of this, of course you end up, well, you can multiply with 2 sigma squared and put it into the regularization parameter. So the negative logarithm of this thing is, of course, the usual quadratic term that you have. And you have some regularization term. This is minus sigma squared times the logarithm of your prior probability. So you can always translate prior probabilities into regularization terms. So if you have Tikhonov, then this would be a square. So you can compute the other way around. Your prior probability would be a Gaussian again, which would give this quadratic term here. Okay, and then you can also again let m tend to infinity and look at the continuous model as an asymptotic model. Typically, instead of a sum, you end up with some integral or something more careful, but typically you just can do this in a very standard way. The interesting thing is you can do this also for a non-Gaussian noise model, same way. So for example, what is trivial is to Laplacian noise, so just take a Gaussian without the squares, do the same computation, and what you get in the end is not something with a square, but you just take an L1 norm in the data. And you can do it for very complicated statistics. You can do it for Poisson statistics. Okay, this is your homework. Look, the formula for Poisson statistics. Take the negative logarithm and see what you get, and you will see you end up with this crazy nonlinear term. This is the so-called Kullback-Leibler divergence that you have to minimize between your data F and Ku. Okay, and then you have regularization, and then there are other crazy multiplicative noise models that appear in some devices, so you have many very nonlinear data terms instead of this usual square that you often have. So in general, you get structures like this. You have a very nonlinear term on the operator, which measures the deviation between the operator and the data, and you have a regularization term. And then there's a lot of challenging things about the mathematical analysis that you do, in particular if you do some crazy regularization like total variation here, which is not completely convex. So if you want to do, for example, error estimates, then you have a lot of troubles here because you don't have any of the nice structures that you have in the linear world, like triangle inequalities and things like this. So there's a lot of things that you can do, and several things are still quite open also in the analysis of these models. Okay, the opposite, just to show you, if you don't do regularization, what people do standardly, and this is the EM algorithm typically, what you would do if you set alpha equals to 0, for example here, so the alpha is not there, so only the first term is here, you could construct a fixed point iteration, which is more or less the multiplicative version of a gradient descent. So in the Gaussian case, you might do gradient descent, which looks like this. Or you do this so-called EM method. This is a multiplicative version for Poisson noise. And you can, if you have nice data, you can produce, like in small animal imaging, you can produce very nice reconstructions. by stopping this iteration method at the right time. The typical idea for iterative regularization is you make a nice iterative process which produces nice images, and if you iterate long, then sometime the noise will come in. So, but you have to stop at the right point so you get nice images before the noise comes in, and this is what is happening here. And the other nice thing about EM is you see this is all multiplicative, so it's easy to figure out that this preserves positivity. So there is no trouble like with all the minus here in the linear world. And you want here density images, and you want in your data term, again, which was a logarithm, you want things that are definitely positive. So you preserve positivity with it. However, you get into troubles when you go to tracers that are not so strong or that are even weaker radioactively. So this is a 2D reconstruction if you take 10,000 detected photons, or 20,000, always 2 of them are detected. If you only have 600 for the same image, this is a simulated image, we get this kind of reconstruction. So you see, you lose a lot with this kind of method. Although this image is obviously pretty easy that we took here, it's just 3 simple holes inside a body. You get very bad reconstructions. So how could you go towards lower dose, which should be nice for the patients, or how could you go towards other tracers like this radioactive water I showed you, which is difficult to detect because it has a low half time, so you miss most of the events because of the detector problems. How could you go there? And one way that we frequently do is total variation methods. Samuli has showed you what is total variation. It was done first time in this Rudi-Noscher-Fatimi model. Sten Oscher is always, for him it's always important to say it was not in the 90s, it was 89. I don't know, for you it's probably not important. And then you get pretty good reconstructions. For example, in denoising, if you take this noisy image, you try to reconstruct, you get this nice reconstruction, which looks reasonably like this one. If you look a bit more careful, maybe in the part you throw away, this is the residual between the noisy and the reconstructed image. I hope you can still see it on the beamer, but you still have all the structures there. So there's a systematic error that these variational regularization, it's not only TV, it's any variational regularization, because you try to make the penalty small, so you introduce a systematic bias. And you see the signal is still there in the part you throw away. So it's a bit too much. Of course, it's not really harmful for just denoising because you can nicely see the cameraman, there's no big trouble. But this gets really more severe when you go to ill-post problems. This effect can really be a strong loss of information, and I will show you some images where this happens. So what we proposed a while ago was to use this kind of augmented Lagrangian or Bregman iteration. The basic idea was simple. If you do denoising, what you see by total variation, you just shrink the image too much. So what we did is we said, okay, we don't take the data, but we add the part we have thrown away, add it back to the data, and then do the same variational problem again. So the idea is you shrink too much, you make the data higher, but you shrink too much, so you get to the right thing roughly. And indeed, with this crazy process, you can show this is a nicely converging iterative regularization method, and you can translate it also to the so-called Bregman iteration. So what you have is you minimize the data term, and then you have some crazy distance. I don't want to go into detail what it is, but there's some crazy distance measured to the last iteration instead of the total variation that you minimize. So you adapt kind of your prior knowledge all the time from the last iterator, so you make the regularization better. And in this way, you can immediately generalize this. If you have another data term, you just put the other data term here and keep the same distance. Just to show you the impact, this is a radioactive sugar measurement in PET. We took as a ground truth what you would usually do. You measure for 20 minutes. And then I told my students, well, let's look how we can do it for, if you only measure 5 minutes, can we get the same results? But of course, my students never do what I tell them. So they took 5 seconds. And what you see is this standard EM reconstruction gets very noisy here, and it's very hard to get the detailed structure of the heart. I'll try to make it again. Then if you do the total variation regularization, you see you get it much better. It looks much more like this. But there are some small parts in the left and right ventricle which you cannot nicely reconstruct here. However, if you do it with this Bregman iteration and stop at the right time, you can perfectly reconstruct all these structure so it's more or less the same quality image that you would get when you measure 20 minutes. So this is of course what makes a doctor really happy, and which makes also the health insurance probably happy if you could do it, because if you can do it in 5 seconds instead of 20 minutes, they can, I don't know, measure many more patients, they can earn much more money, and this is the way they think. We originally thought you can reduce the dose, be nicer to the patients. Turned out the doctors don't think like this, because they say in the US they take the triple dose anyway of what we do, so we don't care. Okay, but the good thing is the health insurance will then pay for regularly for these investigations maybe. Okay, and then we could do it also on this radioactive water scan, and you see in these reconstructions with the MTV. So these were like the images I showed you before. You now see there is really a heart, there is really something, and you even see there is a ventricle, and you can really try to start quantifying how the perfusion of blood through your heart is. Okay, then the last thing I want to not to go into detail, but just mention, if you do dynamic PET, you would of course try to get quantitative results, and you would try to build again PD or ODE models for what is going on inside the heart, and you would try to reconstruct parameters like these reaction coefficients in PDEs from the image data, and maybe do it together with the reconstruction process of the image in order to get good quality. The advantage that you get if you do mathematical modeling is a very nice one here, because instead of reconstructing a 4-dimensional image sequence, you would reconstruct only 3-dimensional parameters. So you effectively, if you have a good mathematical model how the dynamics goes on, you would reduce the dimension, you would make your problem over-determined, and in this way increase a lot the stability. And we could in some cases also apply this to this radioactive water imaging to quantify the cardiac perfusion. So you see this is the standard reconstruction, and this is a model-based reconstruction which looks a bit better. We were not really too much happy about this recent result. Again by Martin Benning in his PhD thesis, again was very encouraging for us in this direction. So you see here, this is a standard reconstruction that is smooth with standard methods. So you see this is completely over-smoothed. You don't see, particularly in the coronal view, it's nice to see, you don't see the ventricle here. It's all over-smoothed of the whole heart. And again, you start seeing what is going on in the left ventricle when you do this time-dependent modeling and make your problem over-determined and get nicer reconstructions. Okay, so you see there is a lot of things that you can do. There's a lot of things which are open in this field, and there's a lot of inverse problems that are worth to be considered in the future. And at this point I stop and thank the people who did the work, in particular the nice movies that I showed, mainly Martin, Jan and Christoph, who is now at UCLA, were responsible for that. And of course I have to thank the many people who were responsible for the really hard work, namely producing all these measurements. This is much harder work than we would think. And I don't mention all the names, just mention we have this special research grant on cardiovascular imaging. So these are mainly the people involved there. And if you want more information, we have some sites where you can download papers or nice movies or just things for kids to play to understand how the research is going on and how important mathematics is also. Thanks.
Are there questions? So in total variation imaging, the images are often blocky. Are there similar type of problems with this Bergman? What are the typical features that?
Well, the images are blocky. You have the staircasing effect. That is definitely true. However, we are less concerned in things like positron emission tomography or things that are really ill-posed, because you just have this loss of information, so you don't care really about the high frequencies somehow. Frequency is a bit more difficult to define when you do total variation. It's not just a singular value frequency, but you have to somehow define the singular values relative to total variation. And it turns out you just cannot anyway get fine structures from these reconstructions if the problem is really ill-posed. And usually in imaging, the staircasing and these blocky problems, they appear in the fine structures, which are nicely varied. So I'm not so much concerned here. We're dealing with main problems where the SNR is just so that we want to see the main structure and the main block in a robust and reliable way, and not go to further small details, because this is probably anyway hopeless.
The questions? Let's thank the speaker again.